Please be seated. We're going to start the session with a talk by Daria. I'll let you the floor.
Thank you. I'm very grateful for the invitation, and I'm happy to present very, very recent work of ours here on this conference. So I wanted to talk about some high-dimensional statistical problem through the prism of statistical physics methods. And so this work was done jointly together with Jean Barbier, whom I suppose you already know, who is an expert in statistical physics, and also Samrit Halahiri and Prag Sur from Harvard University, who are expert on high-dimensional statistics. But in the end, unfortunately, it will be me who is giving the presentation. Unfortunately, because like before coming to ICTP, mostly my talks was about was something like, okay, look at this nice matrix. I can tell something about the eigenvalues, which is good, but it has nothing to do with today's topics. And so I took this opportunity to, while working on this problem, to learn a lot of new and very confusing things at the beginning. And I hope that today, together with me, maybe part of the audience will be also able to learn something new and useful in their future research. So I wanted to start with a plan. So we are going first to talk quite for some time about the models that we were studying. And studying is a broad term, so we're also going to talk about what exactly we want to get from this model. Next, we are going to pass to the first very powerful method from statistical physics, also known as the replica method. Yeah, we are going to try to apply it to our model. Then we are going to talk about the algorithmic side, and we are going to see how the already quite known algorithm, which is called vector approximate message passing algorithm, works for our problem and what is not working. And we are going to finish with trying to prove rigorously whatever we obtained through the replica method. Good. So now let us dive to the model. Okay, we are starting with something very simple and basic. That is the classical linear regression. As you can see, we have some observations y, which obtained by some useful signal beta of the dimension p to what was applying some vector x. We will be talking about x a lot after, but for the moment it's just vector x. And we also added in some Gaussian noise, because what we can do without Gaussian noise. Good. So what we want from this model? We are going to discuss like the typical inference problems. That is, we want to estimate beta from some number of the observation. So how many observations do we need? Since, as you probably noticed, through the name of this talk and the name of the conference, we all of us are in high dimension. So that applies that the number of samples is supposed to be not too big. To be more precise, it's supposed to be exactly as the dimension of the vector that we want to find, so p. So we are assuming that the ratio n over p goes to some constant which is positive. Good. Now we just want to write our model in a more compact way. So on the left, on the left, we have our vector y, which is now n-dimensional. It consists of the observations that we have. And on the right, we have a so-called design matrix Xn. This is a matrix where each row it's our small vector xt. And we have our inference vector b and the vector with ID Gaussian noise. Okay, just let me write here the matrix X, because we are going to talk about it a lot, and I just want you to have it in front of your eyes at any time. So, as I said, it will be the matrix of the dimension n over p. And here, each row of this matrix, it's the vector x1, x2, so on, xn. So, right? Okay. What it can be? It can be many things, because as I said, the linear regression is one of the basic statistical problems, and so it was studied in any possible way with all possible matrices, design matrices xn. So in the beginning, one can assume that this matrix, the design matrix xn, is just a deterministic matrix, and even for this case, there was some Lasso estimates proved. They've found some Lasso estimates, and it was proved that if this matrix xn, if the eigenvalues of this matrix xn possess some specific properties, then we will have good estimates and so on. But after, of course, people said, okay, the deterministic matrix is good, but there are, but in the real world, there are not that many problems that we can model with something that is deterministic, right? So the next step was, okay, so let us now assume that our design matrix is ID Gaussian. It's already a little bit better, probably. And so these matrices, they found a lot of application in some signal processing, information theory. So for example, a lot of information theoretical quantities was found for the case of CDMA matrices, so-called code division multiple access, and compressed sensing. And this is okay, nice. But again, the people who want to apply this problem to something, they again want to have something more complicated, something that have much more structure to it. Because when we have matrix that has just ID entries, there is not much structure to it, right? We want something more. We want to put inside more correlations. And the problem is that like normally in statistical physics, like all methods are very sensitive to this correlation. So once you're passed from something that is ID to something that is correlated, everything becomes much harder, right? But even in this case, in several works, they were able to produce a very nice results to the case when our design matrix xn is rotationally invariant, or right rotationally invariant. It just means that if you multiply our matrix X by some orthogonal matrix on the right, the distribution will not change. Okay, this is already also very nice because obviously the right rotationally invariant matrices, they imply it's a quite big class, and we have a lot of nicely correlated matrices inside. But again, there is always people who are not happy. So especially in some fields from like econometrics or biosciences, as I said, it's very good, but we want something more from this design matrix. For example, we wanted to depend on time. We wanted to have some memory of the previous instances and so on. So one of the easiest way to model such a situation is to take these vectors xi to be a stochastic process. That is, the process that obtained through this equation. So basically now, if you want to find our vector xt plus 1 in the moment t plus 1, we are looking what was at the moment xt, we multiply by some deterministic matrix, we are editing some noise, and voila, we obtained our instance t plus 1. And so after we stack all them together, and we have our design matrix. This type of matrices, they seem to have even more correlations inside them, even more structure, I would say, right? Okay, so all this history was just to justify why we were doing it and what we are doing it. So our problem now is just to take this stochastic model and to try to study it in the sense of information theoretical limits. So we want to find some main quantities, theoretical quantities about this model. Okay. So since we are interested in these information theoretical quantities, The one and main object that usually everyone is interested in is mutual information. In order to describe it, we will start with the posterior distribution, which is like how you find the posterior distribution. Usually, it's a distribution of our signal with respect to the observations that we have, and to find it, we are using the Bayes law, which concedes that this posterior distribution is supposed to be the product of the distribution, the prior distribution of our signal, the true distribution of our signal, multiplied to the distribution of the observation conditionally on all the parameters and signal. And since the distribution of y conditionally on everything else, it's just the Gaussian noise, we can write this distribution just as a Gaussian vector or Gaussian exponent, right? Okay, so now when we have the posterior distribution, we can also define so-called partition function, which is also just the normalizer of this posterior distribution. And two main quantities, this is the mutual information and free energy. So why they together? Just because they're connected through this very simple expression. We know that the normalized mutual information is just the average free energy, bar is averaged, minus some constant. Okay, so the goal of today's talk would be just to find the formula for this mutual information for our model. Okay. Another, and what we also will have almost for free, it's we will find something about the minimal mean square error for our model, which is normally just the expectation of the square of the difference between the ground truth, so like the signal that we had, that we want to find, and it's averaged over a so-called Gibbs measure, which is just the posterior distribution. Okay, another point why everyone is interested in the mutual information is just because it's very correlated to the phase transition of the model, because to be more precise, it's non-analyticity of mutual information, very correlated to, like, it connects straightly to the phase transition moment of the model. Okay, the bottom line, what we need to know is we have our model and we want to find the mutual information of this model. Okay, but if you remember, right, here, what I wanted to show is just that, if you remember our design metrics, right? If you remember our vectors xt, they're created as a Gaussian process, and this matrix A that appears there deterministic, it gives a big impact on the possibility. It gives a big impact on the inference problem, because what is logical is that the more complicated this matrix A, the more structure we have in our design metrics, the harder it's supposed to be to find the true signal beta, right? And so here we see the plot where vertically we have the mean square error, horizontally we have the ratio between the number of the observation and the dimension of our signal. And these three lines, it's just three different mean square errors for three different A's. So the one where it's reaching lambda equal to 0, it's like the easiest one, where it's 1. Then after we pass into like a little bit harder matrix A, and the last one, the green one, it's an even harder one. And so yeah, as we can see, this matrix A, it gives a strong impact on what is the mean square error in the end. We will talk about it a little bit later. For the moment, it's just an overview. Okay, so now we are going to focus on this matrix A. Okay, so the good news is that like before it was just symmetric, and when it's just symmetric, okay, symmetric matrix is good, but it still can be quite painful to study anything about it. So the good news is that since we are focusing only on the mutual information, we don't really care whether we have a symmetric matrix or its diagonalized version. So basically, we can pass from symmetric matrix, we can diagonalize it and take it as it is and study it. So why it's like a two-line proof? Indeed, if A is symmetric, it has this eigenvector decomposition, and then we can see that if you multiply by U transpose the both parts of our equation for xt plus 1, then on the right we will have something new, and we will call this something new x tilde. So it kind of introduce in the new time series. But the main point is that since x is Gaussian and psi is Gaussian, then if we multiply it by some orthogonal matrices, the distribution will not change. So the distribution of x and x tilde and psi x tilde exactly the same, right? Okay, and so why it's important? Because if you write the mutual information, on the very right we wrote the mutual information of beta and the samples obtained through x tilde. Then we can just write, we rewrite x tilde as x multiplied by u. And we notice again, this has exactly the same distribution. So after when we take this condition on x and u, on x tilde, or that it is the same on x and u, we actually can just throw this u away and nothing will change. Again, because the distribution is the same, and anyway, when we condition on x, we also condition on u because u is a part of x, right? Okay. So the bottom line, from this point, we are assuming that A is a diagonal matrix, which is very nice because when it's diagonal matrix, it means that our equation that creates this vectors x, it actually become not one vector equation, but p independent equations. So it means that each coordinate of x is itself a Gaussian process, independent of all other coordinates, right? So if you're looking at our matrix, we remember that like here, we have our coordinates of xt, right? And as we said, we can assume them to be independent one of each other. And so it means that, okay, now we can look at this one, this column, as a Gaussian process. We can look also at this column as another Gaussian process, and so on. So we obtain that our design matrix has independent columns, right? And each of these columns, it's a Gaussian vector with some covariance matrix, right? Okay.
How do you know the transformation? Like, you get your data, you don't know
Yeah, it's yes, we don't know, but the point is that if okay, we have our problem and we have our samples obtained via x, but we know that if we are studying, if we are taking like the same ground truth and we are creating the samples with this x tilde, like the mutual information for this problem and for this problem, it will be the same. So in the end, we chose to study this problem. Yes?
How do you get the mutual information?
Like theoretically or practically?
In practice?
I don't know.
Because it's really obvious.
Yeah, I think, yeah, you don't. Because, yeah, we are very theoretical here. Okay, yeah, so I stopped on a very nice fact that for our design matrix, columns are independent and each column is a Gaussian vector with some covariance matrix, right? Good. So it is very easy to find what is this covariance matrix because if we have this bottom equation, from where we just need to find the variance of each coordinate and the correlation of each coordinate, but in different times points, right? Okay, and so after some very, very, very simple calculation, we can obtain the covariance and the correlations. And actually, it's that easy just because we also assume that the process is stationary. So it means that the distribution do not depend on the time point. So which means, for example, that the correlation between xt plus s, it depends only on s, it do not depend on t. Okay, so putting all this together, we can write our covariance matrix. So now I want you to look at this covariance matrix for a little bit. It looks very nice, very structured. It looks something like many people studied before, right? And it's true, so we know a lot about its eigenvalues, eigenvectors, and a bunch of other properties, but we don't care about that much, that much. In general, as we can see here, we have metrics where on each diagonal we have the same quantity, right? In general, this matrix is called toplex matrices, but this one, it's even nicer because it actually depends only from one parameter, this lambda I, and to obtain like the next diagonal, we just need to multiply by this lambda I, right? We have just degrees of lambda I everywhere. And so this type of matrices, this subclass of toplex matrices called Katz-Murdoch-Shego matrices. And yeah, as I said, we know a lot of things about this, about its vector and properties in general. So the things that we do know, or we do need for this work, it's it's to know the eigenvalue distribution, sorry, and to know something about its eigenvector. So first, let us discuss when n is fixed. Okay, so for the fixed n, what we know? We cannot write explicitly eigenvalues. Like numerically, you can calculate them, but just by hand, it's a little bit, I don't know, I'm not sure that is possible. Okay, so, but we do know that if you want to find its eigenvalue, you will need so-called generating function, which is in the very right corner. This is delta I theta. It's so-called generating function of our matrices with parameter lambda I. And so if you want to find the eigenvalues of our matrices, then you need to take the interval from 0 to p. You need to divide it by n equal intervals. And you will know that in each interval, there is exactly one theta I that if you put it inside this generating function, it will give you the eigenvalue. So what it means, okay, very logically, to assume that, okay, this is for fixed n. So what will become if you take this n to infinity? Like obviously, like all this interval, it kind of will be smoothing out, right? It's very logical to assume that when n goes to infinity, like we can say that probably the eigenvalues, it's like this theta that gives you eigenvalues are probably like just uniformly on this interval 0p, right? And actually this is true. Another good point about this matrix is that for fixed n, the eigenvectors of this matrix, they actually do depend on n and on parameter lambda. But when n goes to infinity, this dependencies kind of disappear from eigenvectors. So in the end, in the limit, all these matrices with different lambdas, with different parameter, they share exactly the same eigenvector space. Why is good to us? Well, it makes it really easy to find like any eigenvalue statistics about like the linear combination of this matrix or like the Russian functions of this matrix or so on. So for example, if we have some matrix F, written here, okay, I wrote it only from one matrices, but we can put there as many matrices of this form as we want with different lambdas. And if this function is like the rational polynomial function, so which means that exactly like the eigenvectors will be preserved. So if you take like the opposite, for example, there's the inverse, or if you take just the linear combination, the eigenvectors will be preserved. So in the limit, if we are interested in just in the normalized trace of this resulting matrix, it means that we can take just this function. Everywhere instead of lambda I, we will put the generating function theta I. So for each lambda, for each parameter lambda, there will be different generating function, of course, but all of them will be of this form. So instead of this matrices, we are just putting the generating function. We are taking interval from 0 to p, and voila, we are done. Which is a good news, and which made the study of this model much easier, because otherwise it would be much harder even to find, like for example, the this normalized trace of lambda 1 plus 1 to lambda 2, right? Okay. So this is what I wanted to remember you about this matrix, and also try to keep in mind this generating function delta. We will meet it after. So now, since again all this lambda talk was just because it's a covariance matrix of our column, what now we can do is that we can present each column as the square root of covariant matrix, right? Multiply by some ID Gaussian vector, right? So why we wanted to do it? It's just because it's nice to just delocalize the random part. We want it to be all independent, and the deterministic part. Okay. So unfortunately, we need to put some additional assumption on matrix A. So okay, we know that it's diagonal, but we also want the number of eigenvalues to not be too big. So we are fixing the number of eigenvalues. We are denoting it by k. And we are assuming that the multiplicity of each eigenvalue, it goes to infinity together with p with the same speed. So basically it means that we want each eigenvalue have more or less the same multiplicity, the same degree of multiplicity, right? Okay, so why we want it? Well, it's just we're assuming that if there are some eigenvalues who are, whose multiplicity of the order 1, then we conjecture that the result will be completely different. So for the moment, we are fixing on the assumption that all eigenvalues has the same degree of multiplicity. Okay, and like we wrote that it's just even. So the multiplicity of each eigenvalue is p over k, but it's not necessarily really. We can just take, we just care that the degree is the same. Okay, so now I just wanted to show you how this model is actually connected to everything that was studied before. So it's very logical when you have some new model to see what will happen if you take the simplest cases, right? So, okay. Let's see what will happen if k is equal to 1. Then we have two possibilities, lambda 0 or lambda not 0. Then when lambda is 0, then all these covariances are just identity, right? And so all our design metrics will be just ID Gaussian. And as I said, it falls in the case that was studied before. So when all the lambdas are equal but not 0, then again, like in each column, we will have exactly the same covariance matrix, right? So we can take it out, and in that, our design matrix will be of the form some deterministic matrix multiplied by some ID Gaussian matrix. And this matrix falls into a class of right rotationally invariant. So it was also studied before. Okay, and finally, the new case, when k is bigger than 1, then due to our assumption, actually what we can do is that we can combine together like all the columns with the same covariance matrix, right? And then here, we will, when we stack together all these columns with ID Gaussians, we will have just some ID Gaussian matrix of dimension P over K by the same n, right? Okay, so in the end, we obtained some block matrix where each block is right rotation invariant. By itself, it's not right rotation invariant, right? And that is what brings something new to all this theory. Okay, so now let us pass to replica calculations. And as I said, it's a well-known method. It's used in many, many applications right now, in not applications, many, many problems right now. So we decided why not to try it also for this model. So the trick itself is very simple. We are presenting our average free entropy as this double limit of a degree of partial function. And we are assuming that, again, not assuming, we are pretending that u is integer, and then we can then we can calculate this degree of partition function. And then also assuming at some point that we can change these limits, exchange these limits, and in the end we will obtain some formula for the free energy, right? So because of all this assuming, replica method is not the most rigorous one, but it's proved itself worthy to try, because in many cases, these conjectures that we obtain through replica method, we were able to prove rigorously using some other methods. Okay, so the point is that we are taking, like first we are pretending that u is integer, we are taking u different replicas from our posterior, and we are writing this degree of partition function as through these replicas. So now the point is that we take to calculate this integral, and we want to, like mostly we want to get rid of all this infinite number of parameters, because each replica, it has like p different parameters to integrate over, right? Okay, so for this, we are introducing some order parameters of efficient statistics. And each of them is the matrix u by u. And there are k such matrices because like this block structures that xn has, it also implies the same block structures kind of on our vector beta, right? So we're kind of assuming that, okay, each block is supposed to be treated differently. So in the end, we need this k different matrices. And each of them, it's overlap of this i's block. Okay. So another important point is that we are assuming that this overlaps, we are assuming that we have this replica symmetric ansatz, which also means that overlaps concentrate. So no matter what replicas we took in the beginning, if we took two different replicas, in the end, the overlap, it will kind of converge to the same quantity. So we're assuming that for each of these matrices, all elements of diagonal will be the same, and all diagonal elements also will be the same. Okay, this also reduces kind of the number of parameters that we need to work with. And so finally, the goal, as I said, it was to calculate the integral and to bring it to something that is much, much simpler, because here we have only 4k parameters after some mysterious transformations. We will have the exponent, and in this exponent, we have this function phi with only 4k parameters that do not depend on anything infinite. There is no n, there is no p, there is no u. So in the end, we are able to use in something like Laplace method to find the critical points of this function phi. And we are assuming that in these critical points, this function will be will have the minimum, and this minimum, it will be exactly our free energy that we wanted to find in the beginning. So I will show you just the final formulas that we obtained through all this calculation. So again, the conjecture is that in the minimum of this function phi, we will have our free energy. And the set of the parameters over which we want to minimize, it is found as the critical points of this function phi in the exponent. And so for our case, after again some simplification, we obtain just system of two case equations. And if you look at this system, we see that like the second equation, it reminds us something, and it exactly reminds us the minimal square error minimization. The minimal is just minimal, it means square error of some very simple channel, because here we have our ground truth. Here we have our averaged over posterior. We take square, we take another average, so it's exactly our MC. And indeed, just to see that it's legit, we took k equal to 1, and then we recovered the result that was obtained before for Gaussian design matrices. And so here, it's just write more explicitly that in this case, our second equation is just a minimal square error of the signal drawn from this much easier channel, scalar channel, where we have square root of r, it's our square root q hat, 1, 2. And that is just Gaussian noise. Okay, so with this replica method, we obtain some conjecture. And now, well, first of all, like we want to try it on some algorithm. So before, for the case when Xn is Gaussian IJ matrix, there was found a very successful algorithm, so-called approximate message passing algorithm. And when for the case when all the lambdas are the same, but not 0, this algorithm was modified in different ways, depends on the prior and so on. So one of the, for our opinion, one of the easiest to implicate and best algorithm was so-called vector approximate message passing algorithm. In this algorithm, like the difference with respect to approximate message passing is that we are not treating like each coordinate of the vectors, but we are treating like all like beta as the vector. Okay, so I really don't have much time, so we are going to just briefly look at the performance, because now what we were trying to do is just to take this FAM algorithm. And first, we were trying to kind of imply this block structure also inside this FAM. But we didn't succeed, because each time when we were thinking that, oh, it definitely should work, in the end, the original FAM worked better. So, for example, like here, it's just, we see the plots for the model when lambda is equal to 1 and all lambdas are the same. So as there is no surprise, everything is matching perfectly. On the top, there is a Gaussian prior, and on the bottom, there is a Rademacher prior. So after we tried, for our model with block design matrices, and for Gaussian prior, it appears that it works pretty well. There is nothing actually there is nothing to make it better. But the problem was with Rademacher prior. So as you can see, in the Rademacher prior, we have this phase transition, and around this phase transition, algorithm really was not stable. So there was bad instances and good instances, and there was much more bad instances, I must say, than good ones. But the bottom line, like outside of this neighborhood of phase transition, it worked very well, because if you look, for example, for at the second plot, where we have the minimal square error versus signal to noise ratio, like it matches very nice. For ratio n over p further from the phase transition, it matches very nicely. Okay, so another curious observation is just, which is kind of logical, that if these lambdas, this eigenvalues lambdas parameters that are close to each other, then even if we have many, we still have a good matching. Because, for example, on the first plot, we have 3 different eigenvalues, but all of them are from interval from 0.9 to 0.7. And even though like this interval is 0.2, it's not that small, especially when you have just interval from 0 to 1 in general, but the matching is still very nice. But when we are taking lambda a little bit further, it's again start to be not very stable. Okay, so yeah, I have just 5 minutes for the interpolation part. It will be very fast. I just wanted to highlight a very key points. And so the adaptive interpolation method, it was created not that long ago by Barbier and Macri. And it was a generalization of a very well-known interpolation method. And so the difference here is that the difference here is that we are taking these continuous interpolation functions that we will be using after, like, to create this critical point set. So here we need again this 2k continuous interpolation function, 2k again because we have this block structure and we have to treat each block kind of separately. Usually the idea is that we are creating a new model which at the time t.0 is matches our old model, and at the time t equal to 1, it's supposed to be something that we can calculate, right? So our new model, it will contain from k plus 1 different channels. And so the first one, here you can see the part from our old model. And here you can see additional part, like here vi is just id vector. And so, r is just like a scalar function, this interpolation function. And the bottom line, like this channel, when t is equal to 1, so we don't have the first part, it's really easy also to calculate the mutual information. And other channels, again, for each block, we will have a separate channel. Here we will have just this beta I0. It's, again, the ith block of the vector beta multiplied by another interpolation function and with another additive ID Gaussian noise. Okay, so on this slide we just presenting again like all the objects but for the new model. And okay, as I said, at t equal to 0 we are having our IP, which is the old mutual information, and at t equal to 1 we have something that we can calculate, and we also have this integral, and we will see after what we want from this integral. So first, let us calculate what is our information at the point 1. So since we have this k plus 1 channel, each channel will give kind of its impact to the mutual information, and so in the end it will be the sum of k plus 1 different mutual informations. So the first part will be coming from these channels, this effective scalar channels, and the second part will be coming from this first equation. Okay, so with the first part, everything is simple, how to find the mutual information. With the second one, we will be using the non-log-dead formula that allows us to find the mutual information for this type of the channels. And it depends only on the empirical spectral distribution of this matrix that is in front of our vectors V. So if we stack all of them together, we will have this block matrix, and we are interested in the spectral distribution of this matrix multiplied by its transpose. Okay, so in the end, what we can say is that this quantity is just the linear combination of our covariance matrices with the coefficients of our interpolation functions. And the mutual information can be presented in this form. And if you look closer to this bottom line, I wanted to remind you what was this formula that we obtained with replica calculations. So this replica potential, the ones that we wanted to minimize to find the free energy, it was exactly of this form. And here you see the first term, it's exactly this I2, R2. And the last term, it's exactly like this, all the sum of the mutual informations of our scalar channels, right? And so what is left is in the middle, this strange term. But like if you see, like here we also have this strange term. So normally we want to match them to each other, right? So in that, this is exactly what we did. So we calculated the derivative, and we have this term, which we will prove to be small, and this term, where we will force to be equal to this extra term from the previous slide. So that is why we are trying to take this interpolation function R2 to be equal to this term R minus average of the overlap. And I think, so, okay, this we will meet. So after we are kind of taking this conjecture, we will obtain the true formula for the mutual information. And here it matches our replica conjecture exactly, except that we have all the integrals inside the mutual information, and before we had them outside of the mutual information. And so the last step, it would be just to prove that through some convex property of the mutual information, we can put them outside, and we can prove that our mutual information is indeed connected to this replica mutual information through this inf sub. So also we know how we're supposed to find it. First, like we need to find the supremum over R2 and then the infinitum of R1. And I think that is it. Thank you. Thank you for attention.
Okay, so we might have time for really one quick question. We are a bit already running late. Yes?
Thanks for the talk. So for these eigenvalues of A, how sensitive it is if I have lambda1 is very close or equal to lambda2? You said that they need to be of the same multiplicity, but can I have something like double multiplicity? Is it fine?
I didn't understand the question. So
like if I have lambda1 is equal to lambda2, basically, so I have one block which is double the size of all the other blocks. Will it everything?
No, but it will be not the double size, because the size in the end, if lambda1 is equal to lambda2, then we have just one block instead of two. Because we just can put it on side and we stack together these columns of ID vectors with these columns of ID vectors, and so.
Okay, so everything will work?
Yeah.
So the only problem is when you really have some eigenvalue of multiplicity 1.
Yeah.
That is the problem.
Yeah. The problem is when it's finite. Yeah.
Okay. Thank you.
Okay, so thank you again. Well, for the interest of time, move on to the next talk. Yes, you could unmute yourself. Perfect. We can hear you, we can see your screen, and we can see your. If you talk again, I think we will see also your video.
If I what? Sorry.
Okay, we see your video. Perfect. So.
Okay. Excellent.
Thank you very much. So the next talk will be given by Antoine, and the floor is yours.
Yeah. So first of all, thank you very much for having me for this presentation. I apologize again for not being able to make it on site. I would have liked to be there, but I feel honored to have the possibility to do it online at least. So today I'd like to talk about random matrix methods for high-dimensional machine learning models, and essentially I will just split this presentation into 3 parts. First, I try to motivate this presentation with an example of why I intend to show you in the following sections, that is to say the linear pencil method. And as the third section, I'll just show you a few examples of how we've used this specific method in our research at EPFL with Nicolas Macris. All right, so let's start with the introduction with the motivational example. So this talk is going to be mostly about random matrix theory, and the question is, why do we need them actually? Well, it seems like random matrices are becoming ubiquitous in machine learning, but it's not always straightforward to use them. And okay, so for instance, we've seen that we can actually understand them through the eyes of replica methods or other statistical physics methods, but I'd like to show you actually another way to deal with them. So just as an example, let's just take the linear model, a very simple toy model that will illustrate what I intend to show you. If we just consider a linear model with a data matrix X of n samples and dimension D, then you just scale the variance of the elements of X as a 1 over D to make sure that everything scales properly when D goes to infinity. And as an output, you just take a linear model with a signal beta star, which has a fixed norm R and corrupted by a noise of variance sigma squared. Then the rich regression model gives you the formula hat beta with the rich regression formula and the penalization term lambda. And an interesting question is to actually characterize the generalization error of this linear model. And well, essentially, this is basically the distance between y and y hat, which is the estimator that you get using the estimator hat beta. And if you develop the terms, then you get some sort of irreducible error sigma squared plus the distance between your estimator hat beta and beta star. Okay, so you can go a little bit beyond that, because what's interesting actually is to take the average error over X and the corrected noise psi here. And usually what people do is to split this tester into two terms, the bias and the variance. So I won't go deep into the technical details to develop these terms, but the thing that I'd like to point out here is that if you expand those terms, essentially you get equation 2 and 3, where you get the trace, well, the expectation over X of the trace of some sort of, I would say, kernel matrix, which is X transpose X plus lambda I to the -1 or to the -2. So for instance, there is to the -2 in the bias term, but for instance, in the second term of the variance, you have two other terms. So what is quite striking in those two terms is that, in fact, those two expressions, they depend on the trace of X transpose X plus lambda I to the -1. Yeah, if you have to the -2, you just take the derivative with respect to lambda, and you get essentially the same formula. So everything seems to depend on this trace of the resolvent of X transpose X. So this is what I call JD of minus lambda. And what's quite well known is that in the high dimensional limit D goes to infinity, those expressions actually have an analytical expression. And okay, this is a quite well-known formula of Marchenko-Pastur from 1967. And this is described by this sort of algebraic equation, or you could think of it as like a degree 2 polynomial in J. And yeah, so if you just take the expression of J given by this Marchenko-Pastur formula, you can actually express the high dimensional limit of the generalization error with all the three parameters that we have seen earlier. That is to say, the norm of the signal beta star, which is R, the variance of the noise sigma, and okay, phi here is the ratio between the number of samples and dimensions, so n over d, and lambda is the penalization. And essentially, you have this analytical formula where you can completely express what's going to be the high dimensional limit of the generalization error. Okay, if you need to calculate G prime, you just take the derivative of your algebraic expression, and then you just have to solve the system, and essentially you get the expression quite easily. Okay, so this is a result that has been known for quite a while now. It's been described quite thoroughly in those two references from Belkin and Hasty. And yeah, so what's quite interesting also with this case is that if, again, you take back the Marchenko-Pastur expression, the derivative of the Marchenko-Pastur algebraic equation, an interesting case that you can actually is the limit when lambda goes to 0. So essentially, you don't consider that you're in the rich regression mode, but more like the least square formula, and you are actually calculating what's going to be your bias and variance in this specific regime. And what's quite nice about this is that the expression actually simplifies quite well. And yeah, so here, for instance, you can see that depending on the aspect ratio of your matrix, so again, your data matrix is of size n over d, so n samples dimension d. And what you can calculate is that your bias term will be 0 above a certain threshold, and your variance term has some sort of exploding regime at the location phi equals 1. And you could think of it as like a primitive form of the double descent phenomenon that people have described thoroughly in machine learning. So once again, with the same references, you can actually have this very nice, simple analytical expression that completely characterizes the generalization error for a linear model. Okay, but now the problem here, I think, is that you would say it's quite a simple model. And actually, how do you go beyond that simple case that Marchenko-Pastur expression can just tackle out of the shelf? And just as an example, there are many different models that you could think about. So you could just go a little bit beyond the linear model, where you consider, for instance, that you're in a teacher-student setting where you have some data coming from the student and coming from the teacher that have some specific covariance matrix sigma. Or you could actually consider that you are using what's called a random feature model, where you have a weight matrix that is frozen at the beginning, and you just want to train the second layer. And still the same question: can you say anything about what's going to be the high dimensional limit of your model? And there are some specific cases that people have been playing around for a while, like the spike linear model, and now people try to go a little bit beyond that case with some matrix denoising model. But the whole question here is there, so we know Marchenko-Pastur, but how do we go beyond that case, and how can we actually rederive potentially the Marchenko-Pastur expression in a simple way? And yeah, actually there is a tool that's called linear pencils, and that I'd like to introduce in the next few slides. Okay, so let's go forward with this specific method. And just as a very simple example of what I want to show you, let's go back to just level 0 of the linear pencil method. So just to give some vocabulary here, when I talk about the TTS transform of a spectral density, this is just a trace of a spectral density of a matrix S. I'm just talking about the trace of S minus the to the I to the minus 1. Sometimes people put the minus sign in some places or the other, but here it's going to be this way. And okay, so maybe the simplest result that we have in random matrices is the one from 1958, where you can actually characterize the TTS transform of the spectral density of a symmetric random matrix. And this is given usually in the form that you can see in the middle in Knot 1, right? This is j squared minus cj plus 1 equals 0. But here I just give you in very specific form, right? Like j equals z minus j to the minus 1, because as you will see, it's actually, it's like the primitive form of linear pencil method that I will describe later on. And in fact, you have to think of it as like, in fact, this is a linear pencil, but a very trivial one of size 1 times 1. I'll go back to this slide later on. And now, before introducing this method, what I'd like to specify is that I will go through 3 different examples. First, the Marchenko-Pastur case, how to rederive Marchenko-Pastur distribution. Then I'm going to talk about the sample covariance matrix. So what if you actually add, say, a deterministic matrix C in your, in those high dimensional matrices that you want to play with. And then we're going to have a look at the random feature kernel. And the main the main thing about those three examples is that they each involve some algebraic expressions of different random matrices. Okay, so let's go forward with the Marchenko-Pastur case. So just to go back to this case, Marchenko-Pastur, what you want to derive is precisely the trace of x transpose x minus z identity to the -1. And now I will try to clarify what really is a linear pencil. A linear pencil is definitely not this expression, x transpose x minus zi, because it's not, as the name suggests, something that's linear in the random matrices that are being considered. But instead, let's construct something that looks like a block matrix that is linear in the random matrix X. So how to do that? Well, it's pretty much like creating some sort of linear equations. You just create some sort of placeholder U1, which is, well, precisely the trace of U1 is precisely what we are looking at. And we actually create another placeholder U2, which is equal to XU1. And well, with just this trick, you actually linearized your whole system. So what I mean by that is that if you check this matrix L here, you multiply it blockwise by different matrices U1, U2, you get back exactly this U1 is equal to x transpose x minus z identity to the -1. And this looks like what I just talked about. It looks like something that's linear in some sense in the random matrix X that we are considering. Now, if you take the inverse of L, so you multiply by L to the -1 on the left-hand side and L to the -1 on the right-hand side, and then you just multiply by another block matrix, identity 0, L to the -1, identity 0, then you get back the term U1 that you are interested in. So what I'm just telling you here is that if we want to actually calculate the trace of U1 in the high dimensional limit d goes to infinity, what you truly want to calculate is actually the trace of L to the -1 at the block location 1, 1. So if you see in parentheses 1, 1 on the right-hand side of a matrix here, it means the block location of a block matrix. Okay, so now we have a linear pencil, and I'll show you how to get back to the Marchenko-Pastur expression. So what we just did here is to encode the matrix that we're interested in into a wider block matrix. So this is the L that we have seen earlier. And then what I will do is to actually extract from this linear pencil the random components. So the random components are, here is just the random matrix X, and you just take what remains, so the deterministic block of your random matrix, and here the only deterministic blocks are -z identity and minus identity. Okay, here there is ID because it's a block of size d times d, and here's a block of size n times n. And then we'll define some sort of covariance structure of those block matrices. So what I mean by that is, if you check this sigma that I define here, so the term that is below 1, 2 is the location of your linear pencil. So 1, 2 is x here, and 2, 1 is x transpose. And those x and x transpose, they will interact with each other in such a way that you actually define the specific components equal to 1. Here, there is this, you could actually define it for each location. So 1, 1 with 1, 2 will be 0, 1, 1 with 1, 1 is 0, sigma 2, 2 with 2, 2 is equal to 0, and so on and so forth. And eventually, the very last ingredient is an operator eta L, which just will multiply a sort of matrix with all these covariance structure that we've defined before. Okay. Now, the thing that we want to calculate here is the trace of L to the -1 at a specific location ij. So this is what I call Jij. If you go back to this expression of L, again, if you just take the short complement, what you see is that if I take L to the -1 at the block location 1, 1, this is precisely X transpose X minus Zi to the -1. So what we really want to calculate is J11. This is the Marchenko-Pasteau expression that we are trying to rederive. And if you apply your operator eta L of J here, well, essentially you get back sigma 1, 2 to 1, J22. So this is just J22, and at the bottom right-hand side, you get J11. And now, finally, the main result of this this presentation, which will be a bit hard to digest, is this following result. I pretend that actually this J function that this J variable matrix that we've described earlier is actually the solution of a sort of fixed point equation where we have two different operators, but okay, we'll dissect a bit this specific expression. So before going deeper into this expression, one thing that I'd like you to realize is that this expression actually looks very much like the one that we have seen earlier with Wigner. So on the left-hand side, you have this J that we were interested in. Here you have some sort of an inverse. Z, you could think of it as like the L0 that we have seen, and J is like this result of the operator eta on J, but it's a block matrix of size 1 times 1, so everything is quite easy. But for larger matrices, then you have those two operators that I will describe just now. So the first operator, eta L tensor dot identity of J. Well, essentially what I want to mean here is that if you are actually giving it some sort of, here it's a 4x4 matrix for the Marchenko-Pasteau case. But if you use this operator, you're actually throwing, well, the application of your operator eta L, and you just add or append a matrix identity Ni if you're in a block where there is as many rows as there are columns. Otherwise, you can just put identity. Otherwise, you just give it 0. So in our case, so let's go back here, right? There is this expression, right? So it's sigma 2 1, sigma 1 2, J22, and J11 here, and you apply again the identity. So you get it. You get the identity here. You get another identity on the other side, and then you just append as well L0. So again L0. This is minus Z, and here there is minus I identity. So this is the expression that we just calculated for Marchenko-Pasteau. And then there is the second, some sort of partial trace operator that is actually just a trace that is applied in the specific block locations where you have squared blocks. So all in all, if you just take back the whole expression that we've talked about, you have J, so this is J11, J22, you apply it J tensor trace of D. You have this expression that we have seen earlier, and if you develop everything, in conclusion, what you have is that you identify the terms on the left-hand side and terms on the right-hand side. So you have the trace of minus Z identity minus J22, right? So this is this matrix to the -1. So you get back minus Z plus J22 to the -1. And for J22, you get minus phi 1 plus J11 to the -1. But again, the term that we are really interested in is actually J of J11. So you just plug in J1, well, the expression of J22 into the expression of J11. Yeah, you rearrange all the terms, and what you get back is just precisely the Marchenko-Pasteau expression that we have seen earlier. So yeah, earlier, I mean the one that we have been playing around here. So okay, it's a bit a lot of hard to digest expressions here, but essentially it's quite a convenient way to get back the results that are quite well known. And as a second example, I'd like to show you that this expression can be used with in a more general context. And one of them is when you have, for instance, to calculate some covariance matrices. So in the real world, usually covariance matrices that you actually calculate are not really coming from the real underlying covariance matrix that you like to have. So for instance, if you're working in finance, an interesting thing is to calculate the covariance matrix of all your assets, but you can only use past data to get it back from. And what that means actually is that there is for sure some errors that actually comes from this sort of sample covariance matrix that you're actually trying to calculate. So just to set things up in the mind. So what I mean is that usually if you want to estimate some covariance matrix from different samples U, so say that you have n samples, usually what you would do is to calculate U transpose, you put some scalings, and essentially if you take this sort of model here that I defined, this is actually the similar to calculating C1 half X transpose C1 half, where X is a random matrix of size n times d, so pretty much like before, but this time the game is to actually trying to calculate what's going to be your eigenvalue distribution of tilde C compared to the real one C that you are truly interested in. So this is precisely the expression that we have at the bottom. So it is C1 half X transpose C1 half. And the question is how to express potentially J with respect to JC. So that would be the Stichius transform of C. To make things simpler, actually, I won't really tackle this specific case, but I will instead calculate X transpose C1 half X. So it's like the reverse expression, but there are some very easy formula to get back from one to the other. So the question that I really want to ask you instead is, can we actually calculate this J of Z, X transpose C, X minus Z identity to the -1 with respect to the Stichius transform of C? So this is really interesting, right? It's like, can we really estimate how our eigenvalues are shifting from C when you have actually your sample covariance matrix that is given from your data? And okay, if you just run the same process that we have seen for Marchenko-Pastur, so basically you just find some sort of linearization method. So again, U1, U2, U3, just think of it as like some placeholder names for some matrices. And what we are actually trying to calculate is the trace of U1. So I pretend that if you invert this block matrix L, and that if you look at the location 1, 1, or even if you actually use the short complement formula, you get back this expression that is defined above. So now we just rerun the same methodology. So there is L0, which is the deterministic part of your linear pencil L. So this is everything but not what's random. So what is random here is just X. So this is discarded in this expression. Then you define some sort of covariance structure of your random matrix. So this is just the interaction of X with X transpose. So X transpose is interacting with X as like sigma 1, 3, 3, 1, and 3, 1, 1, 3. Because the block location 1, 3 is X transpose and 3, 1 is X. So this is set to 1. Then we have again this operator eta L of J, which if you use this expression gives you back J33, J11. Then we just apply the main result. Okay, this slide is a bit horrible, but essentially here you have the right-hand side of the main result, where you just put L0 minus this expression. So it's just taking back this expression L0 minus this expression that has been amplified with some identity blocks. So this is just it. And this is to the -1. You invert it using the Schur complement formula, and eventually you use the main result that we have seen earlier. And what that means is that, in fact, you get that J11 is going to be equal to the trace of this specific block location, and J33 is going to be equal to the trace of this specific block location at the very bottom. Yeah, I won't go much more into the details, but what I want to stress here is that once you solve everything, what you get back is an expression that gives you precisely what I was looking for. That is to say, a connection between Jz and Jc of z, which is the Stick-Chase transform of the matrix C. Okay, this is quite a well-known formula, but what I wanted to show here is that the linear pencil method allows you to just retrieve it in 2 slides. Okay, and the last example that I'd like to show is the linear pencil method applied for the say the random feature model. So that is to say, a model where you consider a first weight matrix W, say, that is given randomly, and then you have a data matrix X that is also random. And again, the question is how to calculate the spectral distribution of this matrix. This for sure will happen if you tackle the random matrix model at some point. And there are different results that show you precisely what's going to be this spectral distribution. But one thing that has been shown is that there is something called the Gaussian equivalence principle that gives a relation between sigma of Wx with something that doesn't depend on the non-linearity of sigma. So you've linearized your activation function sigma. There is a lot of literature around this principle, but technically what happens is that if you want to calculate J of z, what you need to do is just replace sigma of Wx by this linearized version of sigma Wx. And this, again, can be tackled with the linear pencil method. So there are different ways of doing it. I won't do it on the slides because it's going to be horrible, but just the linearization method, how it can be run. One way is to actually define some sort of block matrices. So here you could define mu of W and mu of omega, and here you could define X transpose identity. And in fact, J of z is just the product of those matrices that we've just defined. And so if you use this block matrix L, what you can see using the Schur complement formula is the block location 1, 1 is going to be precisely the product of U, V transpose, V, U transpose. So you get back precisely the expression that you're interested in. And if you flatten everything, basically this is your linear pencil. So it's linear in all the random matrices that we are considering, that is, say, W, X, and omega. Here we have 3 sources of randomness, so you can imagine that your covariance structure is going to be slightly more complicated than the ones that we have seen earlier. So one thing that I'd like to stress is that there is no unique way of using those linear pencils. And there is actually a simpler way of, so here it's a 6x6 linear pencil, but you could actually simplify it further and make it a 4x4 linear pencil. Okay, again, I won't go much more into the details, but essentially this is again the same game where you try to use some placeholders, U0, U1, U2, U3, and you try to linearize as much as possible. And essentially here you can get back to a 1x1, a 4x4 linear pencil. All right, so this is the linear pencil method. I hope that you will have more chances to use that in the future. I think it's quite a nice tool to to play with. And sometimes I think it's even simpler than using, for instance, the replica method. And just as an example of how it can be used, I'll show you different results that we have achieved in the past using precisely just this result. So one model that we actually try to tackle is the some sort of general random feature model, or what's been defined as the Gaussian covariate model from Loureiro in 2021. So it's actually the setting that we've described earlier, where you have a teacher that is given some specific data matrix X and a student that is given another data matrix tilde X. And you could have some specific covariance structure between X and tilde X. And here you could actually create a model that replicates this structure with this ZB and ZA, which is precisely X and tilde X, right? And we could actually wonder what's going to be the generalization error of this model. And this is actually sufficient to describe a whole range of different models, such as the random feature model that we described earlier. Okay, won't describe much more about that, but you could actually define some structure for those matrices A and B that will actually replicate this linearization that we have seen earlier. And if you use this tool and you push it to the limit, what you can get is a very complicated formula at first sight that actually can describe the evolution of the generalization error on this sort of general model. One thing that is quite nice is that if you take the limit of this, so it's actually just a gradient flow over some sort of linear model. So if you take the limit of t goes to infinity, then you should get back what's going to be the result of the least square regression estimator. And this is actually given here. And the nice thing about these results, okay, I don't expect you to have an intuition, but because it's quite a horrible formula. But the thing is, those formula actually match the one from Loureiro in 2021, but where they used a completely different path. Okay. A few examples again. If you use this method to the limit, I think you could actually get some nice heat maps of the evolution of this gradient flow formula. And one thing that you can actually show is, for instance, the triple descent. So if you solve those very complicated algebraic expressions that only computers and numerical simulations can give you precise results, then you can actually predict what's going to be your high-dimensional training and test error at any point in time, and any aspect ratio of your data matrix and weight matrix. So you don't need to run a very high-dimensional model and calculate this for each data point. You can just run the simulations and predict what's going to be the expected error. So here, what you can see is that in some settings, depending on the, for instance, the activation function that you like to consider, you can actually have the first descent, then a second one, and actually you can also design some models, okay, where you can actually have 3 or 4 descents, depending on how you want to specify it, or even n descents. And you can use, again, this whole machinery to really describe how things are evolving. So there was a paper originally from Nakiran in 2020 that described this result empirically. And using this framework, we actually can show that there are some theoretical evidence for the existence of the very same shapes or the very same curves, but using some analytical expressions. Okay, and last but not least, because I described some sort of structured sample covariance matrix C before, you could actually try to use the same principle, but for realistic data sets. So here there is an example for n-list data set. You could actually estimate your covariance matrix using X transpose X, using the whole range of samples that is given in the n-list data set. But you make your prediction on a smaller set. And the nice thing again is that this whole framework would still work with this precise covariance matrix. But okay, there are some ranges where it will start to deviate because you don't have an infinite number of samples to estimate the true covariance matrix, but at least you have some ways to tackle some realistic data sets. So this example actually is also given in the paper from Loureiro. So this is just a replication of the similar results, but using again a different road. All right, so that's it for my presentation. Thank you very much for your attention, and feel free to ask any questions.
Thank you very much, Antoine. Do we have question for Antoine in the assistance?
Thank you. That was very interesting. So all your results derive from that master theorem. And I'm wondering, is the proof of that theorem simple, or is all the ugliness hidden inside? Like, can you tell us a little bit more about this result you were using?
Right. Okay, let me get back to the expression. So, okay, I would say the very first time I've seen actually the expression is from a paper from 2006 from Yufan, etc. The first instance of this master theorem, if you want, was not given in its full form that you are seeing here, but it was given with a proof in a weaker form, I would say. This is using some combinatorics proofs, which are okay, depending on how you feel about it, nice or ugly. But actually, later on, Mingo and Speicher, they gave back the full form in the book in 2017, where again you would find some proofs using some combinatorial methods. There are other proofs that you can actually, well, not proofs, but sketch of proofs, I would say, that are actually given in my PhD thesis, if you are interested. I actually used 3 different ways. One of them is quite nice, I think, using some stochastic calculus, but on a matrix level instead of vector or scalar expression. Basically, you could consider that each element within your random matrix is a sort of stochastic process, and you can derive a sort of heat equation, but on a blockwise range, and you can actually rederive this expression, but it's really hard to make it completely rigorous. But you can. There are some nice ways to rederive it.
Thank you. Marco, you still...
Thanks a lot for the nice talk. So I was wondering, in general, like, what are the limitations of the method, in the sense that perhaps as the model on which you want to compute the statistics of the test error gets more complicated, you need bigger and bigger pencils. So I was wondering if you have an intuition of that. So say I want to do a multi-layer neural net, maybe this scales exponentially in the depth or something like that.
Right, so there is actually, yeah, it's a really interesting question. So as I said, at some point, there is no unique way of calculating your linear pencils. At first, I was doing it this way with a 6x6 linear pencil, but actually you can do it in a 4x4 linear pencil. And at first sight, it doesn't seem like it's going to change a lot, but in fact, the expression that is given from the main theorem will be much simpler if you shrink the size of your linear pencil, even by just a little bit. In fact, the expression yields in some... Okay, if we just go back, for instance, to the Marchenko-Pastor case, it's quite easy, right? You have two algebraic expressions in J11, J22. But if your linear pencil gets bigger and bigger and you just want to derive just one specific quantity like J11, but on a larger scale linear pencil, then suddenly things become a lot more complicated. In fact, actually you would go into another area of mathematics where you try to reduces some sort of polynomials into smaller expressions, but everything gets more complicated when you get a lot more different polynomials, and your expression becomes terrible at some point and really hard to analyze. So definitely, if you have more layers, then you really increase the level of complexity that you get from this expression. The nice thing is that you can still solve them using some numerical methods. So even just a fixed point equation that you just iterate on your computer, you can derive the expressions of your linear pencil. The bad thing is that it becomes harder and harder to interpret your analytical expression as you increase the number of, for instance, of layers of London matrices that you are considering. Yeah.
Thanks a lot.
Any remaining question? Well, if not, we move on. So thank you very much, Antoine, again.
Thank you.
So Yufan, you can unmute yourself and perfect.
Hi.
And you should be able to share your screen.
Okay. Right now?
Yes, we can.
Okay. You can also see the cursor, or?
Yes, we can see also the cursor.
Okay, thank you so much.
Okay, so the last talk of the session will be given by Yufan.
Hello everyone. So today I will talk about a joint work with my advisor, Professor Pragya Shore, on spectrum-aware adjustment, a new debiasing framework with application to principal component regression. The problem we are interested in is very simple and fundamental problem. It's actually just the linear regression. Basically, we have some observations, or like the design matrix X and the hidden signal beta, and also we observe the response Y. So the idea is we want to do inference on beta. In the classical setting where n is much larger than p, we know how to do the inference. You basically just run like ordinary least square regression, and you read the p-values from your R or like whatever statistics package. But a more challenging setting is when you have more covariates than data. In this case, the linear, like OLS, no longer works. For example, like X transpose X is not even invertible. So this is basically the problem we want to consider. A classical approach for like high dimensional setting is like using regularization. You basically just add a penalty term to the quadratic loss, and then you can have your lasso or ridge regression estimator. But the problem is these methods are often designed for prediction. If you want to do inference, then those are not directly applicable, because when you introduce the penalty, you also introduce like a shrinkage bias, and that sort of breaks the normality, in the beta hat. So people have been studying like what's called like one-step estimator, and the idea is to basically make a correction to the regularized estimator so that the shrinkage bias is removed. The idea is very simple. You just like this is the gradient of the quadratic loss. This is the Hessian of the quadratic loss, and you basically just run a Newton-Raphson step at your current estimator beta hat. Then it can be shown that this device estimator is centered at it's basically like the signal plus like Gaussian noise if you are in like effectively a low dimensional setting where you have, for example, you have strong sparsity assumptions in the signal or like the precision matrix. So then you can sort of start asking like, what if I want to consider more general settings, want to relax the sparsity assumption? So the key insight here is actually that you should apply a adjustment coefficient to your Newton-Raphson step, and if you actually choose this adjustment scalar carefully, you can actually maintain the normality around the true signal. So the way people like the state-of-the-art method is what's so-called degrees of freedom adjustment. Basically, the adjustment coefficient is this. You just minus in the denominator, just have one minus. This traced object is actually the degrees of freedom of the regularized estimator. And you just take the effective dimension of your regularized estimator and divide it by n. As we can see here, in the case where your sample size is much larger than your effective dimension, you recover basically the classical one-step estimator we just talked about. Here is an example for lasso. You can see the degrees of freedom in this case is just the number of non-zero entries in your lasso estimator. So if you have like very sparse signal and your lasso is tuned optimally, then you can imagine this correction sort of goes to 0, then you recover the classical one-step estimator. However, so this method is very interesting and gives us like a insight on what one should do for high dimension devising, but there are also like issues. First of all, it really relies on the assumption that the rows of your design matrix, basically your observations, are independent and they follow this normal multivariate normal distribution with covariance sigma. And so it means that your observation cannot have like temporal or spatial dependence, and also you have to know or be able to consistently estimate what the precision matrix would be. So that's actually a very challenging task in high dimension. Usually you don't have that many data to accomplish this. So this is a sort of simple simulations we did for degrees of freedom debiasing when the design matrix are not nice. For example, the first one is you have row and column correlations. So you have dependence across observations. The second one, you have like a low rank, let's say a low rank spike structure. And third one is like you multiply a bunch of like normal entry designs to get matrix together. And third one is you have a sort of a vector auto-regressive rows for your design. The fourth one is like each row you have like a multivariate T distribution. As we can see, if the design is not so nice, this method no longer holds up. So in this talk, we basically just introduced two new ideas. The first one is try to model the design matrix using an alternative random matrix ensemble. So we no longer assume this independent observation assumption, independent Gaussian assumption for the observations. So we use this alternative random matrix ensemble in hope that we no longer have to estimate the sigma, and the step adjustment can account for the spectral characteristic of the data, and that it can be more robust than the Gaussian design assumption. And the second idea is to integrate with the classical PCR to make a more robust debiasing method. Without further ado, this is what our method looks like, basically. As you can see, now I no longer have that sigma inverse pre-multiplied here. Instead, we just run like a simple gradient descent with a scalar adjustment. And the scalar adjustment is solved from this equation, which we can show admit a unique solution. And also, this equation involves only quantities that are directly observable from the problem. Like, for example, we just need the eigenvalues of the sample covariance matrix and the information about the penalty you apply and the regularized estimator. So the key advantage of considering this is that the dependencies in the designs are handled via the scalar adjustment alone. So we no longer need to estimate for the sigma inverse. This is actually, even though the equation looks a bit complicated, this is based on actually a very simple idea. I will show you how to derive this with in the case of ridge estimator. What you do is you write down what the ridge write down the explicit expression for the ridge estimator, and you write down the form that you sort of want this debias estimator to be, basically like ridge plus some step size times your gradient descent, and then you write down the singular value decomposition of your design, and you expand the expression and rearrange it. You arrive at this expression, basically. So in order for this to be debiased, you basically need to make some assumptions on this matrix V, which involves this OI transpose, and the OI is just the eigenvectors of the sample covariance matrix. It's basically impossible if like you allow OI and the eigenvalue di to be any. I mean, if you just allow OI to be anything, it will never work. So we need some assumptions on the OIs. The assumption is basically assume these right singular vectors are drawn uniformly, like from the orthogonal group. Basically, when P is 3, it's like I assume these 3 eigenvectors are like uniformly a rotation, like sort of sampled from a sphere. So it's given this assumption, we have that the expectation of the pair OI transpose to be just like identity pre-multiplied by 1 over P. And then you can write this matrix quantity V like basically as a scalar times beta. Then what you do is you choose the adjustment coefficient so that this scalar equals to 1. This is exactly the spectrum-aware adjustment we propose. And you may wonder what's the connection to the degrees of freedom debiasing. An observation you can make is that when the spectrum of the design converges to Marchenko-Pastur law, this adjustment coefficient is exactly the degrees of freedom adjustment. So what this says is that the degrees of freedom adjustment sort of implicitly assumes that your the spectrum of the sample covariance matrix looks like a Marchenko-Pastur law, which does not necessarily hold up in real data case. In fact, most design matrix have like sample covariance matrix spectrum look very different from Marchenko-Pastur law. So our method is basically, get rid of this assumption and just look at the actual spectrum of the design matrix. For other this can be extended for other penalties using vector approximate message passing technique. We'll not go into detail of that. So basically, under the assumption that the design is right rotation invariant and the principal component or like the eigen values do not diverge, and also that the signal is deterministic or independent of the design, you will be able to have this normality results, which basically saying that this converges to a normal distribution, and you can use this to develop inference procedures with the like false coverage proportion or like guarantees and things like that. So this is this is running our method in the examples, design matrix examples we have shown before. We can see that there is a marked improvement compared to degrees of freedom. And this result can be extended for a single or finite number of coordinates. This is like for marginal inference. If we further assume that the signal has a is exchangeable. Well, this method we applied it for like real data, so it turns out in some cases it still fails, and we sort of summarize like the reasons for these failure are basically the following two. First is that you can have top few eigenvalues to be significantly separated from the bulk of the spectrum, or that or that a small subset of eigenvectors of the design strongly align with the true signal beta. So this basically breaks these two assumptions right here. And we can also see from the ridge example where you want to sort of center the spectrum of V to 1. That's how we chose the adjustment coefficient. But as we can see, if you have like some values to be like significantly larger than the bulk, this sort of unbiased residual component will become very large, making the method like very noisy and unstable. The alignment issue is, if signal perfectly aligns with the top eigenvector, then your expression become this, which basically introduce an inflation bias. So the reason why these are happening is because the assumption we previously made that OI is independent from beta is now broken. So we formally relax these assumptions here by saying that there is a small set of like problematic principal components, so that in the set these principal components can diverge. Everything else we assume they do not diverge, but this set the PCs in the set it can diverge, and also we allow the signal to basically have this aligned component, which essentially aligns with the principal components in this problematic set. So to fix this, to make our method work under these assumptions, we want to use a classical principal component regression. Here is a quick review. You basically just do singular value decomposition for your design, and you select maybe top 5 PCs to retain, and then you do a dimension reduction by doing the spaces transform of your design and using the new design, and you can run your LRS as before, because now like K is less than P, because K is supposed to be like finite number of PCs. And then finally you transform basis to the original basis. But the problem with this method is that it's sort of similar to the ridge and lasso. It incurs a shrinkage bias, because the portion of the signal not aligned with the PCs that you choose is sort of lost in the process. So our idea is basically like we correct this bias by reuse like the low variance PCs that you have discarded. So, we chose like these PCs in K, and the rest we do not throw them away, but to reuse them to form a new regression problem where the new signal is the signal that you have lost. And then we can use spectrum awareness biasing to recover this lost segment, and then we combine with the PCR estimator to form like a full estimator for the like the entire signal with the 2 component. And more concretely, we can look at the algorithm. You basically run like 2 separate algorithm. The first one is you just run classical PCR with the set to be like this problematic set of like aligned PCs or outlier PCs, and then you produce the estimator beta hat AL that consistently estimate the alignment signal component beta AL. And the second step is basically you form this new regression problem with the problematic PCs now removed. This new problem is like you respond your design, and the signal is actually you can check the signal is actually this zeta that we have lost in the first classical PCR procedure. And then you can run the spectrum-aware debiasing for this new data and recover a debiased estimator of the loss signal zeta. And you can put them back together to form a new debiased estimator. And you have the normality guarantee as before. What's the idea behind this kind of method is really like a way to model the design matrix differently. So the proposal is that instead of modeling the entire design matrix as a random matrix, you model like you only model the bulk as the random matrix, but like these outlier PCs or PCs that can align with your signal, you model them deterministically, and you handle them using the classical principal component regression method. And that's basically a more robust way of modeling the design matrix. That's the idea. And we can see here in like a range of even like more challenging scenarios with strong correlations and heterogeneity across rows, this sort of enhanced method is the last row, and it works better than its competitors by significantly. And we also apply this to like design matrices we got from like real design. As you can see, like the advantage of this new method is actually quite obvious. And as a byproduct of our method, we can also have like what we call a alignment test. If you are familiar with like high dimensional method, like approximate message passing, leave one out, things like that, important assumption is that, you know, the signal cannot sort of depend on the design matrix. It cannot have strong alignment, but like there is typically no way to test this because the signal is unknown. So here under our formulation, we are able to actually test this by basically testing if these new i's are zero or not, because when they are zero, they do not align with a principal component. Otherwise, it will be non-zero. So we developed the theory to formulate the test, and you can observe the result here. Basically, the true angle between signal and the principal components are on the bottom, and you can see that it effectively captures like the aligned okay, so these are the PCs, and the angles are to the true signal beta star on the different designs. You can see like this method actually works well. So yeah, so this is the like our result basically. So in summary, we proposed the new debiasing adjustment based on the actual spectrum instead of assuming the spectrum converges to Marchenko-Pastur law, and we leverage right rotational invariant random matrix assumption. The second idea is to use a principal component regression to handle problematic PCs separately. Things we haven't covered in the talk, including like the hypothesis testing procedures and also like the theoretical results about like factor approximate message passing. And the open problem is to prove basically marginal inference result without exchangeability. Yeah, so that concludes my talk. Thank you.
Any question for Yufan?
Thanks for the nice talk. So the numerics that you showed point at some form of universality phenomenon, I guess, because you have the right rotational invariant assumption on the design. So I wonder, given the recent progress in that area, say the papers by you on this, do you think that you can get a universality result also in your setting?
Yeah, I believe so. It's just a matter of doing the proof. It's actually like the right rotational invariant design is sort of like Gaussian Gaussian as for Wigner. The rotational invariant design is for this like this universality class proved in Yui and Shubha Sen's work. Basically, like it's just a matter of theoretically prove these results for the larger universality class, but I think the formulas will remain the same.
Okay, thanks.
Any other question? Okay, so if not, this closes the session. Thank you again, Yufan.
Thank you.
And so the weather is